Section 2.9, Part 2 in Lay's textbook, which is the same as Section 4.5 in Edwards. Now that we know a little bit about vector space and subspace, there are four fundamental subspaces for vector space which involves a matrix. So this is considered this as application of determining a vector space associated with a matrix. So those four fundamental subspace for a matrix are row space, null space, column space of matrix A, and the null space of A transpose. Row space is the same as column space transpose, and the dimension of the row space is what? Same as the rank of the matrix. And notice these guys, row space and null space, happens to be a subspace of Rn. Remember, n is the number of columns of matrix A. Column space and null space happens to be a subspace of vector space Rm. M is the what? The number of rows of the what? Matrix A. So these four fundamental subspaces for a matrix are important subspaces. So we like to kind of go over this topic and go over these subspaces and see how do you determine a basis for these two, and then how do you determine the dimension of these subspaces, and what would be the application of it? Why do we learn this section for? So column space is denoted by C of A. So it's a subspace of Rm, which is also called the range or image of A. Null space is denoted by Na, which is subspace of Rn. Row space is what? Column space transpose. So that means all combinations of rows or all combinations of A transpose. So that would be all, it consists of all linear combinations of the rows of what? Matrix A. And the null space of A transpose, which is also known as left null space of A, it's a subspace of Rm. Keep in mind, once again, row space and null space are what? Subspace of Rn, and column space and null space of A transpose happens to be subspace of Rm. So what's the objective of this section? Objective is what? Find the basis for these particularly row space and column space of a matrix and determine their dimensions. Before we do that, what is a row space? Row space is a subspace of Rn, which is the spanning set of all the what? Of Rn what? Based on the linear combination, what? All linear combinations of rows of A. Column space is set of all possible linear combination of the columns of column vectors of A. So row space is an all possible what? Linear combination of what? Rows of A. And column space happens to be a set of all possible linear combinations of what? Columns of matrix A. So by definition, row space what? Spans what? Is a spanning set, okay, for rows of matrix A, and column space consists of what? Spanning set for columns of matrix A. Incidentally, column space is also known as range or image of the matrix. So basically, those are the definitions of row space and column space. One more time. Row space consists of all linear combinations of rows of matrix A. Column space consists of all linear combinations of what? matrix A. So in turns, they happen to be spanning set for rows and columns of matrix A respectively. So let's go over definitions. Suppose you have a specific example. Suppose you have a 2 by 3. The question is, could you list what? List the rows of A and columns of A. What would those be equal to? Rows of A are 2, 1, 0, 3, negative 1, 2. Columns of A is 2, 3, 1, negative 1, 0, 2. However, when it comes to row space, not rows of A, but row space of A, that would be the spanning set of the rows of the matrix A. In other words, all linear combinations of what? These two vectors. You can create any row of matrix A by constructing what? By forming the linear combination of these two vectors. Okay. In particular, since they are what? Linearly independent, therefore, if they happen to be linearly independent, because by definition they are a spanning set, and if you check and see if they are linearly independent, then they form a dimension for what? For row space of matrix A, which happens to be, in this case, a subspace of R3. Remember, row space is a subspace of R, n as a Nancy. In this case, n is 3. So the row space is a subspace of R3. Column space consists of what? Spanning set of the columns of the matrix. In other words, the columns of each, the matrix A, any column can be written as linear combination of these guys. So they happen to be a spanning set for columns of matrix A, and if they happen to be linearly independent, then we can pretend or call that what? A basis for column space. So in this case, this would form a basis for row space of matrix A. These guys, if they are linearly independent, they form a basis for column space. And the number of vectors in the basis, of course, determines the dimension of the vector space. In this case, you were dealing with column space and row space, which they happen to be a subspace of what? Of Rn and Rm respectively. So the column space is the set of all linear combinations of columns of A, and they happen to be always a subspace of what? Of Rm, and M in this case is 2. So they happen to be, in this case, a subspace of R2. So this would be your vector space for column space, vector space for row space. So how do you find a basis for any given matrix m by n? So here's the example. This would be 3 by 3. So the question is, find a basis for row space and column space and determine the dimensions. Okay, so what you do, you put this in row echelon form, and in row echelon form you kind of select the non-zero, is that right? Non-zero rows in the row echelon form of a matrix. So the basis for row space is non-zero rows of the row echelon form of the matrix. In this case is what? 1, 0, 1, 0, 1, negative 1, 0, 0, 1, because the last one consists of all zeros, so it doesn't count. So it turns out these are linearly independent, and by definition they span. So therefore, the dimension of what? Of the row space happens to be 3. So the dimension of the row space, in this case, happens to be row space. Let me call this RA, happens to be 3 because we have 3 linearly independent vectors in the row space. Now, column space, a basis for column space is a bit tricky now. So what you do the following. You go back to the row space, your row echelon form of the matrix, and see which columns have leading 1, okay? In this case, columns 1 and 2 and 3, they have a leading 1s in row echelon form of matrix A. So what you do, you go back to those corresponding columns and select what? The columns in the original matrix. So once again, for row space, we select the what? Non-zero rows of row echelon form of matrix A. For column space, we go to the row echelon form and see which rows they have which columns they have a leading 1. We go back to the what? Original matrix and choose those corresponding matrix. In this case, 1 and 2 and 3, they all have leading 1s. So we choose the columns 1 and 2 and 3 as our basis for column space. And because you got 3 linearly independent vectors in your what? Column space, therefore the dimension of the column space is 3, but it just so happens we have this nice fact for you to check and see if you got the correct answers for basis for column space and row space, which is the dimension of the row space should match the dimension of column space and should be equal to the rank of A. And in this example, they are all equal to 3. So let me just do one more example just to clarify how to find a basis. So the question is given this, find a basis for row space of A and column space of A and determine what? Their dimensions or dimensions, right? Here's the matrix, it's 3 by 4. So what do? Keep in mind, once again, row space is a subspace of R4, which is the same as Rn. Remember, 4 is your n. Column space is a subspace of R3, which is Rm. M is 3. Put the matrix in row echelon form, you got this. The basis, the vectors in a basis for row space is the what? Non-zero what? Rows in the row echelon form. So list the first 2 rows of row echelon form of matrix A. Okay, and remember this is a subspace of R4. That's why you got 2 4-dimensional vectors in the basis of row space. To determine the basis for column space, go back to the row echelon form and see which columns have leading 1. In this case, columns 1 and 2 has leading 1, so go back to the original matrix and select those 2 corresponding what? Columns as your what? Vectors in the basis of the column space. So this would be a what? A subspace of R what? 3. In other words, you have 2 3-dimensional vectors in the column space. Then again, check and see the dimension of the row space of A should match the dimension of the column space of A, should be exactly the same as rank of the original matrix. In this case, each of these bases have 2 vectors in them. So therefore, the dimension of the row space, which is the same as dimension of the column space, happens to be 2, and that checks the fact here, which we went over a minute ago. Finally, we have something called null space. Null means neutral. So that's also what? A subspace of Rn. Remember, n is the number of columns, so it's the subspace of Rn. That would be like what? Set of all n tuples of real numbers. So what's the definition of null space? Null space is the set of solutions for a homogeneous system of equations. So the set of solutions for a homogeneous system of equation, which happens to be a subspace of Rn, is called the null space and denoted by n of A. Okay, So this is the set notation for the definition. So it consists of all vectors in Rn such that they happen to be the solution of this homogeneous system of equations, and it's always a subspace of Rn. Terminology, the dimension of what? Null space of what? A, matrix A. Sometimes it's called the nullity of matrix A. So the dimension of the null space of matrix A, sometimes it's called the nullity of matrix A, depending which textbook you're looking at. So let's do an example. Here's a matrix, which is 3 by 3. The question is find the null space. Find the null space of A. In other words, what would be the null space of A equal to? So what do? Because it's a solution of homogeneous system of equations, so immediately what? Form this augmented matrix. Okay. Augment the matrix, the given matrix with 0 vector, and find the solution, because by definition what? The null space consists of all vectors which they happen to be the solution to this homogeneous system of equations, linear equations. So find the solution, which in this case, notice you put the augmented matrix in row echelon form. Uh, Only columns 1 and 2 they have leading one, column 3 doesn't, so it has to be a free variable. Therefore, you have infinite many solutions, and this is how the solutions look like. However, if you factor out the t, you get negative 2, 2, and here you should get what? 1. Is that right? So what happens is, because everything else is what? Is is the scalar multiple of this vector, namely negative 2, 1. So therefore, guess what? A basis for the null space is consists of this vector only. Therefore, we only have one linearly independent vector. So the dimension of the what? Null space, which is the same as dimension of the what? Solution space, is equal to 1, not infinity, just 1, because you only have one linearly independent vector in the basis of the null space. So everything else is just a scalar multiple. Remember, t is a real number. Here is a nice theorem. The rank of A plus what? Dimension of the nullity or null space is always equal to n. N is the number of columns. So this is called rank nullity theorem. Rank of A plus dimension of the null space, which is the same as nullity of A. So sometimes this is just called nullity of A, should always add up to the number of columns of A. So this keep this handy formula in mind to check your answers. Okay, so what's the purpose of column space and row space? Why are we learning this section? Well, let's say you have a system of non-homogeneous linear equation. If B happens to be not in column space of A, then system is inconsistent and there is no solution. But what does that mean? That means you cannot write B as a linear combinations of columns of what? Matrix A. If you could write B as a linear combinations of what? Columns of A, then the system is what? Consistent. And now you would have a unique solution if and only if the dimension of column space matches n. Okay, remember n is the number of columns of matrix A. And you have infinite many solutions if the dimension of the column space is less than n. So there goes why we need column space. On the other hand, if your system is homogeneous, that means you have 0 on the right side and the rank of A is the same as n. So remember, n is the number of columns. Then the system will have only trivial solution. In other words, the null space will only have zero vector in it. So the dimension of the row space is zero, which is also known as nullity of A. Okay, because you will have a trivial solution. On the other hand, if the rank of A is R, but R is less than number of variables in your system, then the what system of homogeneous equation has infinite many solutions, all of which can be obtained by writing the linear combination of all those vectors up to and including n minus r. In other words, all these vectors up to and including n minus 1 are linearly independent set of n minus r solutions, excuse me, to your homogeneous system of equation. And that's where you can use what? Null space. You can relate the null space to what? To solutions of what? System of linear equation. Thank you.